Welcome back. We're going to continue our discussion on Lewis structures by now diving into what we call molecular geometry. We're also going to be talking about something called electron geometry. So make sure that you are ready to talk about both. We're going to be talking about molecular geometry and electron geometry. Now, before we get started, let's make sure we know what this means. Molecular or electron geometry are both terms that are only applicable for molecules. They are not applicable for anything else. We're not talking about ionic compounds here. We are only talking about molecules. Okay? Now, when we're talking about molecular geometry, we want to talk about something called the valence shell electron pair repulsion theory. This is called VSEPR, is the abbreviation for this. VSEPR. Now, VSEPR pretty much just tells us that we have to be able to geometrically arrange atoms around the central atom determined by the repulsion that's happening by electron pairs and by other atoms, right? So in other words, if we were to draw just a shape of something on a piece of paper, say for example, like we had drawn carbon tetrachloride before, it's not really going to be shaped that way in real life. That's what VSEPR says. Because we can get these, if we're looking at the distance between these two things, the distance between these two things is only about a 90-degree angle. But we're talking about a 2D space when we're drawing on a piece of paper. VSEPR is something that imagines molecules in 3 dimensions. Like how good can we get it if we're in 3 dimensions? So now, if we're talking about 3 dimensions, we could probably get those carbons and those chlorines a little bit away from each other. Because remember, electrons, although they kind of deal with being near each other, they would like to be away if they can. So that's what VSEPR is all about. Electron pairs take positions such that repulsion between them are at a minimum, and they have plenty of space to themselves. That's the idea. So there are a lot of different molecular geometries, and there are a lot of different electron geometries. Now understand, each one has a different group, and you can kind of consider each group as separated based on the number of things attached to the center atom. And we are going to represent the central atom in this situation as the letter A. It doesn't really mean anything, and it doesn't represent a particular element, but we are going to use the letter A to represent any central atom. We are also going to use the letter X to represent anything attached to the central atom. We are also going to talk about lone pairs, because lone pairs often determine molecular geometry. Lone pairs attached to the central atom will be replaced by the letter E. Now, remember, there is a difference between electron geometry and molecular geometry. Molecular geometry, you can consider it like the shape in 3D space, based on both lone pairs and on the things bonded to the center atom. Whereas the electron configuration is mostly determined by just the number of things bound to the central atom. It's not as complicated. And I'll show you what I mean as we continue to keep going. Let's talk about our first category, which we would refer to as linear. So linear is our first electron geometry group. And the electron geometry group for linear can be shown as the structure of AX2. Now if we were to draw this out, we would have an X here, an A here, and an X here. And if we were to think about how far away one X is from the other X, you would be able to consider that this is a bond angle of 180 degrees. Okay, simple enough. It's called linear because it looks like a line. So, trigonal planar is our second electron geometry group. Now, we can represent trigonal planar as AX3. That means we have an A here, an X here, an X here, and an X here. Notice that it did not draw them kind of like in a T shape, because again, we're trying to get those X's as far away from each other as possible. These angles are all equal, and you can probably guess what those angles are. This is going to be 120 degrees in between all of them. So now let's talk about the derivative. Okay, the first derivative that we're going to see is AX2E. So whenever we see a derivative, all we have to think about is how we're, instead of putting an element on the central atom, we are replacing one of those elements with a lone pair. So if you look at the base electron geometry, which is trigonal planar, instead of putting an element on the top, I'm going to put a lone pair on the top. That's all. And now I'm going to continue to put x's. But what's interesting about these shapes is that the lone pairs actually push harder down on the bonds because the lone pairs want lots of space themselves. So when they push down on those bonds, they actually change the bond angle of this particular structure. And now we have this new structure that we call bent. Okay, so this is what we would consider a molecular geometry, bent. But if I were to look at a shape like this, that is AX2E, and I was asked to tell the electron geometry and the molecular geometry, they are different things. Molecular geometry is based on lone pairs. So based on the molecular geometry, this shape would be called bent. But the electron geometry is simply based on the number of things attached to the center atom. So for example, I have 3 things attached to the center atom. Everything that has 3 things attached to the center atom has the same electron geometry. It's trigonal planar. That's how it works. So kind of keep that in mind as we continue to go forward. So let's now look at our next shape. It's called tetrahedral. Tetrahedral is AX4. So we're getting a little more complicated now. We have A here, we have X here. We don't really have to draw this one as best as we can. We can do this better, but it requires these things called dashes and wedges where we're trying to show things in a 3D space. And let's not worry about it too much. Let's not get all sweaty about it. This bond angle here is 109.5. You're going to have to believe me. I know that it looks like a 90-degree angle, but I can prove it to you with shapes to show you that it's actually not that way. But again, we're just trying not to get all too wrapped around the shape. 2 derivatives this time. We have AX3E, which again, all we're doing is we are replacing one of those elements with a lone pair. When we replace that top lone pair, because that lone pair needs all that space to itself, what it actually does is it pushes those other elements down away from it. And it makes a new shape that we call trigonal pyramidal or trigonal pyramidal. I've heard it both ways in my life. So trigonal pyramidal. What it does is that you can kind of imagine it being somewhat flat like this, and the lone pairs are up here, and the lone pairs go poof, and they push it down into a trigonal pyramid, like a pyramid shape, okay? And then we have our second derivative, which is AX2E2. So we're going to take another one of those things attached to the central atom, and we're going to replace it with lone pairs. In this situation, we're going to kind of put both of the lone pairs at the top, kind of at an angle. And then we put the elements pushed down like this. And this shape is bent again. That should be somewhat of a familiar shape because that's actually the shape of water. That's what water looks like. Water is a bent molecule. So if you've ever seen water in a 3D space, sometimes it kind of has this this Mickey Mouse look where there's a large orb in the middle and then 2 smaller orbs on the end. That's what bent looks like. And we can make bent 2 different ways. We can make it in AX2E or AX2E2. Okay, but again, no matter the shape or the structure, anything that has 4 things attached to the central atom has the same electron geometry, and that electron geometry would be called tetrahedral. Okay, let's keep going. So now we have trigonal bipyramidal is our next one. You probably are picking up on the pattern at this point. This is AX5. Now this is when things get a little complicated. You have to kind of have a little bit of a spatial understanding here. If we imagine that these 2 things are going up and down like a pole, then we have another set of elements that kind of go in and out like a plate. So one of them's kind of flat like this and the other one's like this. And we have 2 different bond angles here. From that flat pole down to the plate, this is a 90-degree angle, so anything on the equator, or excuse me, from the end to the equator, that's 90 degrees. But then anything going on the equator, so anything on that plate, those are 120 degrees, just like trigonal planar. So you have to kind of imagine it like it's a trigonal planar element with a stick through it. That's pretty much what trigonal bipyramidal is. You can imagine the more we have on the center atom, oftentimes the more electron configurations or derivatives, molecular geometries we can have. This time we have AX4E. AX4E looks like this. We take one of those X's and we replace it. And this gives us a shape called seesaw, you know, like at a playground. And then we have AX3E2, which if we take off more, I'm going to kind of draw this one over here because I ran out of space a little bit. Now we have something called T-shaped. So this actually is a T-shape. That's why we don't draw a trigonal planar in a T-shape. It's already been taken. And then we have AX2E3. And this kind of goes all the way back around again. So now let's replace another set of X's. This goes all the way back around again, and this is actually linear. So we have so many lone pairs around that center atom that it's actually straightening out the entire structure, and we're linear again. All right, one more. This is octahedral. It's a little confusing because you would think that it would be called like hexahedral because there's 6 things attached, but it's octahedral, okay? Octahedral has this kind of star shape. Looks like this. We have 6 things attached to the central atom, okay? And each one of those bonds has a 90-degree angle. There are only 2 derivatives of octahedral. There are AX5E, which is the same, except we're going to take that bottom X off. And what we get is this kind of interesting shape that we call square pyramid. Imagine it like the bottom is a base and there's one sticking up at the top, square pyramid. And then we have AX4E2, and that is where we have lone pairs on both the top and on the bottom. And this one is what we call square planar. Now imagine that we have 2 sets of lone pairs on the top and the bottom, and it kind of flattens out everything, making just a square shape. Now, again, electron geometry is different than molecular geometry. All of these shapes, regardless, would all have the same electron geometry, octahedral, because they all have 6 things attached to the center atom. But based on the lone pairs, they would all have different molecular geometries. The next part in the note says, see the Lewis structures in section 4 in order to get a little practice. Let's go back there. And now let us go and add molecular geometries and electron geometries to those so we can practice. All right, here we are. So this is pretty easy. Let's just label each one. I'm going to do it kind of in a different color so we know. I'm going to label it electron geometry and molecular geometry. So remember, electron geometry is really easy. You just count the number of things that are attached and boom, that's the electron geometry. Sometimes they are the same, sometimes they're not. So you just have to be careful. So for example, if we're looking at CCl4, I have 4 things attached to the center atom, which means the electron geometry has to be tetrahedral. So I got to spell that out, tetrahedral, just like that. The molecular geometry, because there are no lone pairs, is then the same as the electron geometry. It's also tetrahedral. Okay? Now, let's look at something like NF3. If we're looking at NF3, the electron geometry for NF3 is again tetrahedral because we have 4 things attached to the center atom. But the molecular geometry is different now because of those lone pairs. The molecular geometry has changed. If we look at our skeletal structures, which is why we do that, it helps us kind of point out which one's which. We see that this has 3 things attached and 1 set of lone pairs. So this is what we call trigonal pyramidal. I'm going to kind of abbreviate a little bit because I don't have as much space. And then we move on. H2S, the electron geometry is again tetrahedral. We have 4 things attached to the center atom. The molecular geometry, however, in this situation is bent because we have two lone pairs. F2, O2, and N2, they all have linear geometries, whether that be electron geometry or molecular geometry. Anytime you just see a line and it's just two elements, it's always just going to be linear for both molecular geometry and electron geometry. So, why don't you take a second and think about this one? You can pause me if you need to. Well, three things attached to the central atom, so I'm going to call that trigonal planar. And there are no lone pairs, so the molecular geometry is the same thing as the electron geometry, trigonal planar. Easy as that. Why don't you give the top few a try? Look them over and see what you get for the different geometries. Go all the way up to beryllium chloride, because it's just kind of matching shapes, right? I think you can handle it. Go all the way up to beryllium chloride, and then I'll help you out with C2H6. Go for it. Whew, this is what I got. So octahedral for the first one, trigonal bipyramidal for the next one, tetrahedral for the ion, tetrahedral for the electron geometry for SO3-2. However, trigonal pyramid for the molecular geometry, trigonal planar for SO3, and linear for BeCl2. So if we're looking at C2H6, you might think, well, how the heck am I going to figure this one out? Just look at each central atom. So carbon has four things attached around it. The other carbon has four things attached around it. So this one's also going to be tetrahedral for both situations. And I'm just going to put molecular geometry. I'm just going to do it like that because it's the same. Now, if we're looking at xenon tetrafluoride, this is one of those things. Just count up the number of things attached. Oh, my fluorine lost its little thing there. Just count up the number of things attached to the center atom. There is 6 things attached to the center atom. So its electron geometry is octahedral. But then you would want to count the number of things that are lone pairs and look at the derivatives. So we know that there's one derivative of octahedral that has 2 lone pairs. We call that square planar. Try ICl3 and also do SO2. Why not? And then we'll be done. For ICl3, we are trigonal bipyramidal because we have 5 things attached to the central atom for our electron geometry. But our molecular geometry is what we would call T-shaped. And then for SO2, we are trigonal planar because we have 3 things attached. And we are bent because of that one lone pair on the top. And that's about it. So we will continue on with our conversation next time. We'll just continue to talk about structures. We'll see you there.